Determine what two whole numbers the square root is between without using a calculator or table. Then use a calculator or table to check. To figure out about how big the square root of 72 is, it's helpful to compare it to this list of square roots. This isn't a list of random square roots. These are some of the first several square roots that simplify perfectly to whole numbers. To determine what two whole numbers the square root of 72 will lie between, we can compare the square root of 72 to some of the numbers in the list. For example, we could compare it to the square root of 36. The square root of 72 is larger than the square root of 36. Let's continue our way down the list. The square root of 72 is larger than the square root of 49 and larger than the square root of 64. But the square root of 72 is smaller than the square root of 81. So if the square root of 72 is larger than the square root of 64 and smaller than the square root of 81, then the square root of 72 must lie between these two square roots. Since these two square roots simplify to 8 and 9, the square root of 72 must be between 8 and 9. And this is our answer. But the question also says to use a calculator or table to check. We'll use a calculator. The square root feature on some calculators can be a little bit tricky because sometimes, such as this calculator, it doesn't get its own button. Rather, it's written above the x squared button. So to activate this feature, you'll need to first press the second feature button before you press the x squared button. If we use this feature to find the square root of 72, our calculator gives us this result. Notice that the whole number is 8. Since there's a decimal portion, that tells us that this number is bigger than 8, and yet it's smaller than 9, which confirms our answer that the square root of 72 is between 8 and 9. A standard city block is a square with each side measuring 117 yards. Find the length of the diagonal of a city block. We can begin by making a diagram. The question says that each side of this square is 117 yards. It's asking us to find the length of the diagonal. If we recognize that this diagonal cuts our square into two right triangles, then we can use the Pythagorean theorem to solve. But first, let's label our diagram. It's customary when you have a right triangle to put a small square in the corner of the right angle. And since this is a square, all four sides of this square are the same length. And we're asked to find the diagonal. We now have the information we need to start using the Pythagorean theorem. But before we do that, some people prefer to rewrite the diagram. So here's the triangle, and it's customary to use variables of a, b, and c for the sides. A is one of the legs, b is the other leg, and c is the hypotenuse. The Pythagorean theorem is often memorized as a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. If you're looking for a or b, then it's nice to have those on the left. But since we're looking for c, it's sometimes nice to write it in the other order, where we have the hypotenuse on the left. C squared equals A squared plus B squared. It's actually your preference, but this is the way that we'll proceed for this problem. Notice that the hypotenuse is by itself squared, and on the other side we have the legs squared and added. We're now ready to substitute in our values. Since the legs are both 117, we get C squared equals 117 squared plus 117 squared. We can use our calculator to help us with this. It'll square 117, and then it'll help us to add. Notice that we have C squared equals 27,378. This is C squared on the left, but we're looking for C. So we have to take the square root of the 27,378. Notice that from the beginning of this problem, we had C squared on the left. And then, at this step, we changed it to a C. To do so, we also then have to take the square root of the value on the right. We then can use our calculator, and it gives us this value. Notice that we're being asked to round to the nearest hundredth, which is 2 decimal places to the right of the decimal point. To do so, we look at the digit to the right of the 6, which I've circled here, and it tells us what to do with the 6. Since the digit that we've circled is 4 or less, it tells us we need to round down and keep the 6. We get C equals 165.46. Had that 2 been 5 or greater, we would have needed to round up to 7. Finally, we need to consider the units. Since the question said that the city block was 117 yards, then the units for our answer will also be in yards. And that's the final answer. In summary, if a city block is a square with each side measuring 117 yards, then the distance across diagonally will be 165.46 yards. Tell which set or sets the number -17 belongs to. Natural numbers, whole numbers, integers, rational numbers, irrational numbers, or real numbers. Beginning with the natural numbers, notice that they start at 1 and go up without any fractions or decimals. Since -17 is negative and the natural numbers do not contain any negatives, -17 does not belong to the natural numbers. Let's consider the whole numbers. Notice that the whole numbers contain all the natural numbers and 0. As a way to remember it, some people notice that the 0 looks like a whole, spelled differently, but the trick works. Since the whole numbers do not contain any negatives, -17 does not belong to the whole numbers. Now let's look at the integers. The integers contain all the natural numbers and whole numbers, but they also include the negative direction, -1, -2, -3, -4, etc. Therefore, -17 belongs to the integers. For the rational numbers, the definition can look a bit intimidating, so let's take a look. The definition shows that rational numbers include numbers of the form a over b, where a and b are integers, and b is not equal to 0 because you are not allowed to have 0 in the denominator. We will come back to that later, but first I want to mention that it can be helpful to think about the rational numbers and the irrational numbers at the same time. because it turns out that any given number has to be in one of two situations. If the number belongs to the rational numbers, then that number does not belong to the irrational numbers. Or if the number belongs to the irrational numbers, the number does not belong to the rational numbers. So negative 17 must go in one, but only one, of these two sets. So because we mentioned that it's a over b as a fraction, it might look like negative 17 is not a fraction and therefore not a rational number. But the number doesn't have to be written in fraction form at that time. We are allowed to change it to fractional form by putting it over 1. And now we can look at the top and the bottom of this fraction and ask if they're both integers. And yes, negative 17 we determined was an integer. 1 is an integer, but not 0. And therefore, negative 17 belongs to the rational numbers. Which means we must be in this situation. We said if a number belongs to the rational numbers, then it does not belong to the irrational numbers. So negative 17 does not belong to the irrational numbers. Finally, we need to consider the real numbers. Notice this definition says it's any number that's rational or irrational. Well, we just finished saying that in this course, every number we're considering is in the rational numbers or the irrational numbers, but not both. And therefore, every number we study will belong to the real numbers. So negative 17 belongs to the real numbers. Negative 17 belonged to 3 of these sets and didn't belong to 3 others of these sets. So this is our final answer. Determine whether the statement is true or false. Pi over 4 is a rational number. Also, determine whether the statement is true or false. Every real number is also a rational number. To work with these sets, it's helpful to have their definitions handy, so I've copied them down here. And part A says, pi over 4 is a rational number. If we think about pi over 4 and the definition for rational numbers, notice that pi over 4 is of the form a over b. However, the definition goes on to say that a and b are both integers. 4 is an integer, but pi is not an integer. So therefore, this number is not fitting the definition of rational numbers. It's not an integer over an integer. So the statement is false. Pi over 4 is a rational number? No, pi over 4 is not a rational number. Part B, every real number is also a rational number. Notice that the definition of real numbers contains all rational numbers. So every rational number is a real number. But our statement is not worded that way. It says every real number is also a rational number. Is every real number also a rational number? Well, no. The definition of real numbers indicates that they also contain the irrational numbers. So the statement, every real number is also a rational number, is false. Let's take a look at a few particular examples to illustrate this. I've listed some numbers, 2/3, pi, and radical 2, and notice that 2/3 is rational. It's a fraction where the top and the bottom are both integers. But pi and radical 2 are irrational because they cannot be written as the ratio of 2 integers. 2/3 belongs in the set of rationals and in the set of reals. Pi and radical 2 belong in the set of the real numbers, but not in the rationals. So there are at least some numbers that are real, but not also rational. So our statement is false.